Welcome back. Part 2 of lecture Work, Energy and Power. In the last lecture, we discussed about the work, energy and power, and in this chapter, that is part 2, we will be talking of examples of energy conversion, conservative and non-conservative forces, elastic and inelastic collision. Let's see the conservation of mechanical energy during the free fall of the body. For this, let us consider this a mass m which has been taken at a height h2 and it has been shifted upwards through h1 so that it reaches the height h above the earth's surface. Here the total energy is given by the potential energy which is equal to mg and the height it has attained equal to h. This height h, it is the sum of height h1 plus the height h2 which is given by equation h equal to h1 plus h2. Let us calculate the total energy at point P. In this case, the total energy at P is the sum of potential energy due to height h2 and the kinetic energy because this mass has fallen down through a distance h1. We have calculated the potential energy at h2 equal to mg h2 by using the Newton's law of motion, which is given by v square is equal to u square plus 2gs. Here u is the initial speed at the height h and that is u is equal to 0 and s is the distance it has moved and that is equal to h1. Then we have putting these values in the above equation, we get v square is equal to 2gh1. Therefore, the kinetic energy at h2 is equal to mv square by 2 equal to mgh1. We got this by putting the value of v square equal to 2gh1. Therefore, the energy at point h2 is the sum total of kinetic energy plus potential energy which is equal to mgh1 plus mgh2 equal to mgh. Let us talk about the conservation of mass energy in nuclear reactions. When nuclear energy is obtained by transformation of mass into energy. Hence, in nuclear reactions, the law of conservation of mass and the law of conservation of energy merge into single law of conservation of mass and energy. There is another case in which there is a conservation of mechanical energy for mass oscillating on a spring. For this case, let us consider there is a spring which is attached to a mass m and then there is another mass which is moving with a velocity v. It is fixed rigidly to this wall and this mass is moving towards this spring. Here initially, that is before collision, there is the sum total of energy is equal to kinetic energy plus the potential energy. Since this is moving with a mass m with a velocity v, therefore we have a kinetic energy as half mv square. But this thing is in a relaxed state, there is no extension as well as compression in this case, therefore the potential energy of the spring is 0. So, the total energy before collision is half mv square. But when this mass strikes this spring, it compresses it to the maximum limit, that is xm. In this case, again we have a total energy as a sum of kinetic energy plus potential energy after the collision. Here this mass has come to the rest, therefore we have kinetic energy equal to 0 and potential energy, it is maximum for a spring, that is given by half kxm square. So, according to the law that total energy is conserved, we have kinetic energy plus potential energy before collision is equal to kinetic energy plus potential energy after collision and net result we have half mv square equal to half kxm square. So, this is another example of conservation of mechanical energy for a mass oscillating on a spring. Let us talk about the conservative forces. There are forces in which they have the property that the work done by the conservative force is independent of the path taken. What is the path taken? In this case, there is a point A, we take it to the point B, and we can take two paths. There could be a path 1 and there could be a path 2. So, work done along path A is given by WAB, and the work done along path A to B through this path is given by WAB2. So, when AB1 is equal to WAB2, then we say that this is an example of conservative force. This means that it is independent of the path taken. WAB along 1 is equal to WAB along 2. The work done by conservative force on an object is 0 when the object moves around a closed path and return back to its starting point. Example for the conservative forces are gravitational force, elastic force and electrostatic force. Let's talk about the non-conservative forces. As you can see in the figure, the non-conservative forces, there are two paths taken. One is a horizontal path, that is A to B, which is a straight line, and another one is a path 2, which is a curved path. So, a mass is taken from point A to point B through two paths. But here the force of friction is coming into play, and the work done in moving the body from A and B along the two paths are dependent on the path, and they are actually depend on the path taken. The force of friction is a good example of non-conservative force. There are two types of collisions which are coming into play whenever moving bodies collide, and then these type of collisions are classified into two categories, that is elastic and inelastic collision. The system is closed, that is no external force act on it. In which to study the elastic and the inelastic collision, we always take a closed system in which no external force act on it. Then there is a condition called as head-on collision. What is head-on collision is that colliding bodies move along the line joining their centers. And in this case, we have two types of collision, that is perfectly elastic and the perfectly inelastic collision. What is perfectly elastic collision? Where the force of traction between the two bodies is conservative. Here the kinetic energy is conserved. And what is perfectly inelastic collision? Here the two colliding bodies stick together afterwards, that is after collision, and the best example for this is a bullet embedded in the target. But in perfectly inelastic collision, the kinetic energy is not conserved. Now we will come to the elastic collision. We have taken two masses MA, and there is another body which has a mass m, and it is denoted by MB. MA is moving with the velocity VAI towards the right, and MB is moving with the velocity VBI towards the left. Here before collision, that is before these two masses collide, we have an initial momentum. Initial momentum is given by the sum of this momentum of this ball, that is MAVAI, and then we have the momentum of this ball, that is MBVBI. Once we have the collision, that is this is after the collision, the both of masses move in the different direction and with the different velocity, which is given by VA final velocity, and this is VB final velocity. So, after collision, the final momentum is given by MAVAF plus MBVBF. Similarly, we can have an expression for initial kinetic energy. We have a kinetic energy as half mVAI whole square plus half MBVBI whole square. For this, that is after collision, we have a final kinetic energy given by half MAVAF square plus half MBVBF square. Now, applying the law of conservation of momentum on before collision and after collision, we have, that is the momentum remains conserved. This means that the initial momentum is equal to final momentum, which is given by MAVAI plus MBVBI equal to MAVAF plus MBVBF. This is given by equation 1. Applying law of conservation of kinetic energy. This means that the kinetic energy of this whole system remains conserved. This means that initial kinetic energy should be equal to the final kinetic energy, which is given by half MVVAI square plus half MBVBI square. It is equal to half MAVAF square plus half MBVBF square, which is denoted by equation 2. There are two knowns. This is a known quantity. Even we know VAI, VBI, both are the known quantities. The only unknown quantities are VAF and VBF. So, we have to solve these two equations for VAF and the BAF, which are not known to us. Just avoiding the tedious calculation on the board, we get this result, that is, I am writing the solution on the board, which is given by this, that is VBF, that is velocity of B final minus velocity of A final, is equal to negative of VBI minus VAI bracket close. So, this is denoted by another equation, that is 3. The unknown quantity, that is velocity of the ball A, that is the final velocity, it is given by 2 mb VBI divided by MA plus MB plus VAI MA minus MB MA plus MB, that is given by equation 4. Similarly, we calculated VBF. So, VBF is equal to negative of 2 MA VAI upon MA plus MB plus VBI MB minus MA and MA plus MB. Here, a point to be noted is that all these quantities are given to us, and we can have different values and different condition on these collisions put. We can always calculate, that is VAF and BBF. So, this means that we can always come out with special cases of elastic collision, and we have different conditions put on it, and the result, that is the future, is known to us just simply by these equations. So, let us discuss the case 1. This is a special case of elastic collision, that is mass of ball A is equal to mass of ball B equal to m, and then we have VAF is equal to VBI. Similarly, what do we get in putting this equation in the second equation? We get VBF equal to VAI. This means that if two identical balls collide head on, their velocities after collision get interchanged. That is, if A was moving with the velocity VAI, then after collision it moves with the velocity VBF. Similarly, if VBI was the velocity of mass MB, then after collision it is moving with the velocity VAF. So, simply their velocities are interchanged. Let us consider the special case when the ball of mass MB is at rest, that is VBI is equal to 0. Then this means that what happens when we substitute this equation, that is VBI, in this 0, put this here 0. So, this term becomes 0, and we have from this equation, this mass and mass cancels out, we have VBF equal to VAI. So, we can say that after collision A comes to rest and B moves with the velocity A before collision. This means that if we have two masses in which the bigger mass is at rest and the smaller one approaches it with the velocity V, then after collision the B starts moving with the velocity of A and A comes to the rest. Then we have another case, that is case 2, in which the mass of ball B is much greater than mass of ball A. And here again we have the ball at rest, that is VBI equal to 0. When we substitute these values in the equation 4 and 5, then we get the two values, and that values are given as VAF is equal to minus VAI and VBF equal to 0. So, this means that after collision the heavy particle is at rest and the lighter particle returns back on its path. So, in a way we can say that the lighter particle, it returned back on its path, that is the momentum has been transferred to it and it was unable to move the heavy particle at rest and it moves with the same velocity with which it approached. So, this happens when a child hits a wall with a ball and just we can see the ball bounces back with the same velocity with which it strikes the wall. So, this elastic and inelastic collisions, they find applications in many areas of physics, that is about the atoms in every mechanical engineering and all, and this is how it has been of special case that we have discussed in elastic and inelastic collision. Now, since we have discussed all these special cases of elastic collision as well as the inelastic collision, let us solve one numerical problem. Let us say we have a numerical, that is a ball of A of mass 2 kg, it collides head on with a ball B of mass 4 kg. So, we have a ball A, it is colliding with the ball B. Now, our A is moving in the positive x direction, therefore, we have shown this direction, that is A is moving with the velocity 50 meter per second, and B is moving in the negative x direction, that is B is moving in the negative x direction with the velocity 40 meter per second. Now, what are the velocities of A and B after collision? And it is given that the collision is elastic. Since we have discussed that all these elastic collision, they follow this rule, that the equations that we have derived by the law of conservation of momentum as well as the energy. We have VAF is equal to 2 mb VBI upon MA plus MB, VAI MA minus MB upon MA plus MB, that is equation 4. So, from this equation we are substituting the value. We have 2 and then that is MB is the mass of the ball B, we have taken it as 4. Then there is the initial velocity of ball B which is minus 40 because it is moving in the negative x direction, minus initial velocity of ball A, that is 50, and MA minus MB is minus 2, divided by MA plus B, that is 4 plus 2 6, and this is again MA plus MB, that is 6. While solving this equation, we have minus 320 by 6 plus 100 by 6, we get the final velocity of ball A to be minus 35. What this negative sign signifies? It says that after collision, this ball moves in the negative x direction with the velocity minus 35, that is 35. So, this means the initial ball was having a velocity 50 and after collision it is moving with a velocity 35, that too in the opposite direction. So, there is a decrease in the speed of the ball. Now, let us consider the equation number 5, which gives you the value of ball, that is the final velocity of the ball B after collision. It is given by minus 2 MA VAI upon MA plus MB plus VBI MB minus MA plus MB. While substituting these values in this equation 5, we get the velocity of B, that is the final velocity, it is equal to 2 into 50 by 6 plus minus 40, 4 minus 2 upon 6. While solving, we get positive 20 meter per second. So, after collision, the ball is now moving towards the right, that is the positive x direction, and it has again there is a loss in the velocity, it has come down to 20 meter per second. So, in this solution, this numerical problem, it says that the ball A returns back with a velocity 35 meter per second and ball B moves with a velocity 20 meter per second. So, I hope you understand the value of elastic collision as well as the inelastic collision that we encountered in our daily lives, and there is a decrease in the velocity, there is all the laws are being obeyed, and still we have dissipative forces which are coming into play and there are difference in the velocities. In this chapter of work energy part 2, you understood about the conservative forces, non-conservative forces. Then we have elastic collision, inelastic collision, the special cases of the elastic collision. We solved one numerical problem. I hope you understand this lecture very well, and we welcome a feedback from you and meet you in the next lecture. Thank you.